All right, everyone, let's start this afternoon's session. Our first speaker is Firoozeh from Fraunhofer. She's specialized in computer algebra systems, and today she will tell us how Julia drives the development of high-performance computing tools.
So, hi everyone. Thank you for being here. Thanks for the nice introduction. And before I continue, disclaimer: if anyone wants to already start digging into our code and opening up issues on GitHub, that's the QR code you want to follow. And if you want to follow the slides live with me, the QR code down there should take you to the Google Slides link. And hopefully I didn't mix up the two QR codes, but you would see at least the GitHub one at a later stage as well. So again, welcome. I'm going to talk about DistributedWorkflow.jl. This is a fairly new package in Julia, which is trying to interface a distributed workflow manager so that you don't have to leave Julia, preferably, for as long as possible. Okay. So before I introduce the package, let me introduce the main characters who were involved in this package. So I am a PhD student. I started my PhD at Fraunhofer on a stipend, which is where I came across the underlying distributed workflow management system. By profession, I am a theoretical mathematician, an algebraic and tropical geometer. So very, very domain-specific research. And I'm associated with the RPTU University in Kaiserslautern. So how did I get introduced to Julia in the first place? It was peak of the pandemic. I started my PhD, and I had to now suddenly learn about computer algebra systems, specifically in Julia. And the specific one I was working with or trying to learn is called Oscar. I am not sure if people have heard of it, but it's fairly well known amongst mathematicians. And with whatever documentation that was available, I started learning about Oscar and how to use Julia and different features of Julia and Oscar. And at the same time, I started working on understanding the underlying workflow management system and how to use it. Not being a computer scientist, I would say both these two aspects were a steep curve for me. I'm comfortable with one. I won't tell you which one now, but maybe you'll find out yourself. So before moving on, again, let me get some of the basic definitions out of the way. What is a distributed workflow manager? According to Wikipedia, a workflow management system provides an infrastructure for the setup, performance, and monitoring of a defined sequence of tasks arranged as a workflow application. Luckily, the underlying theoretical basis of the workflow management system is based on the mathematical concepts of Petri nets. So that got me very excited. I was like, yay, Petri nets, I know what they are. So what are Petri nets? A Petri net is a directed bipartite graph that has two types of elements called places and transitions. The circular objects you see on the right of the screen are known as the places, and the rectangular boxes are the transitions, and they are connected to each other through an arc. No two places can connect to each other unless they go through a transition, hence bipartite graph. And I was like, cool, I understand this. This is very easy. As a mathematician, what's the problem? Well, the implementation of it. So, okay. Then I started learning about how to use the underlying workflow manager on its own, because I need to understand that before I can use it in my research. So what would be the steps involved in writing a hello world example, which is a very basic, simple place, transition place, where the input place goes into the transition, does some hello world thing, and gives you an output token or an output result that you can read. So the first step is you have to come up with an application structure for your initial application. Then we have to create an executor, design the workflow, because it's based on Petri nets. That is what would launch later on. Create your workflow launcher, because the workflow needs to know how to launch it. And compile and execute. 5 easy steps. What's the problem there? I wouldn't go into the details of all the 5 steps because we are here to talk about DistributedWorkflow.jl and not the underlying workflow manager, but I would still like to show you the first 2 steps, how to set up the application structure and how to create the executor. And I would like to remind you at this point that this is pure C++ code. There's no Julia involved at this point. So we start with a simple main CPP file. Okay, you can read the contents or you can read it later on the Google Slides, no problem, or on their how to use page. There is some more information coming in and maybe some more. And yeah, so these were the first 2 steps. And if right now you want to run away from this room, I don't blame you, but hang in there. I promise things are going to change. So as I said, these are the first 2 steps. We haven't even designed the workflow yet. And if you're scared of C++, I introduce you to the Petri net, which you have to write as a XML file yourself manually. You can still do it if you're like, yeah, this package sounds like it's for noobs. I can work on it myself. Why do I need this package? I encourage you to go ahead. I don't have any problems with it. But for others like me who are scared of everything that you saw, and the first time I saw all of this and I understood how to use it, this was pretty much my reaction. Emotional damage. And if I've caused emotional damage here, I'm sorry for that, but as I said, things are about to change. So, what were my frequently asked questions to my project and PhD supervisor constantly when I was learning how to do this? Number 1, do I have to write this over and over again for each new application? That was just hello world. And can't I simplify the interface to make it easy to use for people like me or others who are not computer scientists? The answer to the first one is yes. So you have to write it again, and the complexity increases with the larger your workflow becomes. Luckily for us, the answer to the second question is also yes. So introducing to you DistributedWorkflow.jl. However, currently we have some small initial setup that we have to do before I dive into the Julia code. So you would require at the moment a spec installation. If you already have it, you can skip step number 1. Otherwise, you can go to their getting started page and set it up. Next, you can go to our GitHub repository, download the respective binary from our release tag for your appropriate Linux distribution. Extract the binaries in a target location. Here I call it Zeta. You are free to call it whatever you like. It is the location where all your binaries will be extracted. And hopefully everything goes well and the computer science gods are not angry with me yet. We can do a spec load and the binaries are loaded and we are ready to use. We are ready to use the package. And I'm so glad I came to this conference this year because I got to meet a lot of HPC experts, Julia HPC experts, and binary builder experts. So if what I heard and learned from them works out for me, I have to try it out. If I manage to build it with the binary builder, this step will be removed for you entirely, and you can do exactly, you can download the package exactly how you download any other Julia package. So for now, minor inconvenience, but it should be removed soon or in the future. I don't promise the time right now. Okay, so let's go to Julia and download it. Again, currently it's in the registration process. Once registered, you can just go to the package manager and say add distributed workflow, and it should download it as any other Julia package. At the moment, you have to give it the GitHub URL, and it should work. If it doesn't, please contact me. I'll see what I did wrong there. But it works. I checked it tonight and last night and in the morning. So once we have the package downloaded, now what do those 5 steps we saw earlier look like for us? Well, for distributed workflow, again, you need your Julia application. You need to know what do you want to compute in parallel. You need, based on your application, to design the Petri net workflow. By staying in Julia, no XML code required here. There's a nice Petri net structure, and everything will be done for you, and you would not know what's happening behind the doors. You can if you want to open up the source code. Okay. If you are not relying on the serializer provided by Julia, you're free to use your own quirky serializer format. I tried it with JLD2, or you have some other serializer format because you might think that Julia's native serializer is not sufficient for the data types you have. We are completely serializer agnostic, so you can use it. You just have to provide it with a serializer descriptor. We will look at the example soon. You have to set up the workflow launcher, which is also done within Julia, and then you submit the job. So let's proceed. You do using distributed workflow, and hopefully you see this nice ASCII Petri net as our welcome banner. And let's say the Hello Julia example or Hello World example I want to execute is a simple function which takes 2 inputs, 2 outputs, does something in the middle. I don't really care, it's just an example. But what I care about specifically, to know that I'm not going crazy, is to pass a sanity check which says, if you are reading this, your application worked. Celebrate. I should add that. And it would return you the output string, which is your sanity check, and your result. You don't have to pass the sanity check every time. It's just for the example. So how would the Petri net look in this case if you want to draw it by hand? It would have 2 input places, P1 and P2, connected to 1 transition. So the transition corresponds to your function. And it has the sanity check output and your result output. And the way to write this Petri net in Julia would be to, can I use the pointer here? Oh yeah. So you can create an empty Petri net object, give it a name. I called it Hello Julia, so it tells you how many ports, places, transitions you have. And then you populate it by giving your places. So place, for the lack of imagination, input file 1, input file 2, output file 1, file 2. The transition, which would run your function. And how do you want to connect them? You want to connect the transition T with place 1 and 2 with the input arcs, and 3 and 4 with the output arcs. And how do you want your data to be transferred? You want the 2 places to take the input tokens and throw out the output tokens. These are connecting your workflow to the outside world from where it would access your serialized data and return you serialized data. So once you've connected, you can see that here it's populated now with 4 ports, places, and 1 transition. And you can view this before even compiling it to make sure everything is okay. You can use our view function and do something like this. This is a PNG format file, but you can also create it in any of your favorite file formats. I used GraphViz, so whatever format GraphViz allows, this can do. And if you're happy with it, you see, okay, yes, I have all the connections in the right places, I can continue with the setup of my workflow launcher because I want to use the native serializer. We can move ahead. If you're not happy with it, you made a mistake, we have a convenient remove function from which you can remove your place or arc or transition and reconnect it. You don't have to start over again. So setting up the workflow launcher, so you have to store your Petri net either in a file, which is what I like to do. I like to place them in a script so I can locate them later, or you can do it in the REPL and compile the workflow in wherever you want. I created a temporary directory because once my application is done, I can delete all of that. And all of this is done for you once you run the compile workflow. If everything went well, you should see the success workflow compiled message. If not, you should see a error which should not be that difficult to debug, but I will add a troubleshooting page eventually to the repo. Okay, so the workflow is compiled. Now let's set up the workflow launcher. For that, we first need a client who would know how you want your execution to perform. You add the number of workers. It's a small example, so I took one worker. Where do you want your node file to be? And currently, I tested it locally because I don't want my sysadmins to be angry at me by using expensive cluster resources. So you can test it locally before acquiring resources. So you set it to local. It initiates the client. You get some message from the underlying workflow manager. And then you have to do some other. So this is where you actually create the workflow launcher. So you have to populate the input, output ports, the function name that should be executed, which it looks up in your application file, and the configuration of your application and configuration of your workflow. At the moment, you have to pass a serialized data stored in a file. So the input file here, this is also, by the way, part of the examples in our repository, where I have the initial inputs stored as the native, stored using the native serializer. And you have to pass it as a vector to your submit function. So this is pretty much all you have to do to set up the workflow launcher. And once it's done, you can go ahead and submit your workflow with the client you started and the workflow description you provided and what input variables you had. And again, hopefully everything goes well. You get one thing I forgot to mention, which is in the previous slide, you can also tell it where to store your output. So your output directory can be set by you. And it would return you the file names of your outputs. And I gave it a variable name submitfunc, so I don't have to write the entire string. And using Serializer, you can simply deserialize the functions, the return values, and yay, success. And at this point, you're like, but you said it's serializer agnostic, and you're just showing me the example for the native serializer. So if someone noticed, I skipped on step 3, because for the native one, you don't have to describe a serializer. I forgot what I called it, but serializer descriptor, thank you. So let's have a serializer descriptor. I used Oscar because, so as I said, I tested it with JLD2. It works just like the Oscar example. However, the Oscar serializer is a special serializer, so I wanted to see if it works with that as well. And since I'm a mathematician and I'm going to use Oscar, mostly I want, again, it's the reasons this package was created was out of selfish reasons. So I tell the Julia native serializer how to save and load using Oscar, and this is the only thing that needs to be added to your application script where you have your application functions connecting to the transitions. And nothing else needs to change. Your workflow remains the same, your config remains the same. The only thing that changes now is your serialized data. Since you're now asking to be serializing it with Oscar, you have to store your input parameters with Oscar Serializer somewhere on your system or a shared file system. And then if you run the submit function, it should run fine. And if you try to deserialize it using now the native serializer, yay, it worked, because it can't deserialize, because we didn't want to deserialize, and the native serializer cannot deserialize Oscar data. However, Oscar works. Oscar is reading the data that was generated. So when I saw this, I can't tell you how happy I was when this showed up on my screen for the first time. And I'm still just as surprised when I see it every time. So yeah, this is your basic Hello World example. And now I move to some of the features due to lack of time. So some of the important features of this package is ease of use. I will insist on ease of use at every part of this package. We reduce the complexity, as I don't think I need to say more about it. It is serializer agnostic, as I just proved it with the Oscar serializer. The API, the public API is completely documented, and most of the functions also have examples. I'm in process of adding examples to the ones where it's missing. You can locally test it before acquiring expensive resources. You can generate your Petri nets within Julia, visualize it in any format you like, convert your Petri net to the XML file without even writing a single line of XML. Submit your job through Julia, and if you want to log your job, you can also do that. There's an example, again, available online, which I didn't show here. You can create a logging port where the information would be transferred. And again, check out our examples to have a better idea of what's happening. Upcoming features, we will soon have notebook support for viewing workflows. This was actually done during this week, and it's fairly new. We could technically merge it, being a two-people team, but we still insist on following proper protocol and going through the proper release process. So as soon as that's done, this should be available. I'll show you an example of it. It's pretty cool soon. And you would get specialized transitions, again, to make it easier to use. More workflow examples will be following soon, or you can also look at the underlying workflow manager. There they have a whole database of different workflows they've used, but it's all in XML format, just warning you. There will be even more convenience functions coming in, not just for your workflows, but also to launch the workflow and configure your application. So even better UI and many other features that I would skip over for now. As any other package, we are also not short of limitations. Some of our limitations are coming from the underlying workflow manager, which is we currently only recommend you to run this for long-running processes. Otherwise, the overhead is too large for a smaller process. The official support for the underlying package is for Ubuntu 20 and 22. However, I manually right now test it, and at some point I'll automate the process. We provide you with, I believe, 6 different Linux distros to use it with. This is only available currently because, again, the underlying workflow manager only supports Linux distributions, and most clusters run Linux, so Mac and Windows are not supported. However, if you want to test it on Mac and support Mac and Windows, I highly recommend using containers, and you can run your favorite Linux distro there. And currently it requires a shared file system. And to summarize, it is easy to use. You can generate, view, compile workflows within Julia. It's fully documented. You can locally test stuff. Binaries are available. And for more, please go to our GitHub our GitHub page on distributed workflow. And as promised, here is the initial example. This is a Jupyter example, so you can do a show workflow, and it would show you the workflow in the notebook. And to find out more, please scan the QR code. If there are any questions, I'm happy to answer them.
Any questions? Yeah, very good. So what are you actually compiling during that one phase? Like you said you took the XML file and it was being generating some C++ code, or what's happening there?
You mean the compilation?
Yeah, the compilation step.
Oh, wait, I can go to it, I think. This.
Yeah.
Yes, so it created, if you look at the extension, it's an XPNet file, which you never really touched or created. You did. So when you do an include hello Julia, maybe I should have shown it there. So I have a function called JenerateWorkflow. I did the name. I don't think the name changed. So currently the API is a little unstable because we are version 0. But I try not to change it too much, but I think it's called JenerateWorkflow. When you say JenerateWorkflow and pass the PetriNet structure, it would give you the XPNet file, and you just use the compile workflow and give it the XPNet file and tell it to do the C++ compilation for you.
Okay, thanks.
Yeah. There.
This PetriNet stuff looks pretty useful, maybe also on its own with the visualization. And I guess there's maybe also some, like Dagger does something similar. So might it make sense to like factor this out into a separate package that's independent of the workflow backend, just this graph representation and some operations on PetriNets and that stuff?
I would say maybe. So the main issue, well, maybe one issue that I can think on the spot is how would I call it? Because when we were trying to name this package, I came across a package called PetriNet already, but that's not really a generic PetriNet compilation. It's doing some physics and I either ODEs or PDEs. So that name was taken, and if we separate it, then it might cause confusion for people who want to use the PetriNet as a generic workflow, and the ones who are coming from the physics end who want to use it specifically for those ODEs. I mean, sure, the physics people can use this, but they might be surprised by it. Yeah.
Maybe another question, if I may. Currently, you have to build the PetriNet in Julia with these connect operations and so on, right? So would it be a possibility to like have a macro or generated function that takes a chunk of Julia code, looks at assignments, and basically builds the net from that? Like taking calls as transitions and assignments as places, and then builds the nets that's implicit in the code?
So I would say I'm not sure if Julia can. So I don't know how to do that in Julia, but I can try to learn it. But we are trying to provide you with like convenience functions which have pre-built workflows. So you can say, okay, this is my function, that's the workflow, because my function matches that workflow. So you don't have to create the PetriNet.
All right. Let's thank the speaker again.